Hello everybody, and welcome to our video on trigonometric integrals and substitution. So we're just going to jump straight in with an example that will illustrate the kind of thought process that we use for a lot of trigonometric integrals. Not all, but at least a lot of them. So we're going to take a look at the integral of sine cubed of x dx. Now, in this case, I don't already have any approach to use for this, at least not directly, because I can't use a substitution if I try to do u equals sine of x. I don't have a cosine of x expression here to use for my du, so that's not going to work. Now, I could possibly make integration by parts work, and we've seen power reduction formulas for sine and cosine, so that's possible, but there's also an easier path for this problem, and so we're going to take a look at that. So what I'm going to do here is just rewrite sine cubed as sine squared of x times sine of x dx. And once I write it in that way, I can recall that I can always convert expressions involving sine squared or cosine squared into expressions involving the other function squared. So we know that sine squared of theta plus cosine squared of theta is 1, so we can always write sine squared of theta is 1 minus cosine squared of theta, or cosine squared of theta is 1 minus sine squared of theta. So the reason that this is valuable is because I know that the derivative for sine is cosine and the derivative for cosine is negative sine. And so when I can convert between those two expressions, I can write this thing in a way where I can do a u substitution. So I'm going to replace sine squared of x with 1 minus cosine squared of x times sine of x dx. And now we see, oh, I can let cosine of x be my u. And if u is cosine of x, then my du for my substitution is negative sine of x dx. In other words, negative du equals sine of x dx. So this becomes 1 minus u squared times negative du. Now, of course, when I write negative du, I really mean negative 1 du, and I can distribute that 1 across these terms. And then the u squared, the negative u squared becomes a positive u squared, and the positive 1 becomes a negative 1, so I'll rewrite this as u squared minus 1 du. And now I take my antiderivative normally, so I get u cubed over 3 minus u plus a constant, and finally substitute back in. So we substitute cosine of x back in for u. We get cosine cubed of x minus cosine of x plus c. So the whole key here is just keeping in mind that we can always replace even powers of sine or cosine with an expression involving even powers of the other function. So let's summarize this strategy. So integrating powers of sine and cosine of x. So if cosine of x has an odd power, then save a factor of cosine and use cosine squared of x equals 1 minus sine squared of x to rewrite the remaining factors. Then substitute in u equals sine of x. If sine of x has an odd power, then save a factor of sine and use sine squared of x equals 1 minus cosine squared of x to rewrite the remaining factors. Substitute u equals cosine of x. So this option B here is what we did here. We had sine cubed. We saved a factor of sine by rewriting it as sine squared of x times sine of x dx. And then we replaced sine squared with 1 minus cosine squared of x. And after rewriting, we were able to do a normal substitution of u equals cosine of x and integrate. Now, if neither of these has an odd power, so in this expression, the reason we could make this work on this integral was because I could pull out one of those factors of sine of x and use that for my du. But that only works because the power here for sine of x is odd. So if neither sine of x or cosine of x have odd powers, in other words, if the powers of both sine of x and cosine of x are even in the expression, then we have to use half angle and power reducing formulas to rewrite the integral. So you should recall from trigonometry, the sine squared of x is 1/2 times 1 minus cosine of 2x, and cosine squared of x is 1/2 times 1 plus cosine of 2x. And you're going to use these formulas fairly often, so if you don't have these memorized now, this is a good one to throw on some note cards and drill a bit because they are really, really important. Also, sometimes sine of x times cosine of x equals 1/2 sine of 2x, which is just a rewriting of the double angle formula for sine, can be a helpful identity if you just have that power, single power of sine and cosine. Okay, so let's take a look at one more example here before we move on to, well, I guess we'll do 2 more examples before the next topic. Let's see, so sine squared of x times cosine cubed of x dx. So cosine has the odd power, so that's the one that I can pull a factor off of. So I'll rewrite this as sine squared of x times cosine squared of x times cosine of x dx. And remember, this expression is what I'm trying to make my du, right? So that means u is going to need to be sine of x. So I need to replace the cosine squared of x. And of course, we know that cosine squared of x is 1 minus sine squared of x. So we're going to use that Pythagorean identity and rewrite this as sine squared of x times 1 minus sine squared of x times cosine of x dx. And we do our u substitution. U is sine of x, so du is cosine of x dx. And that becomes the integral of u squared times 1 minus u squared times du. Now I just multiply the u squared across. I get u squared minus u to the 4th du. And take antiderivatives normally, right? This is our power rule, so we get u to the 3rd over 3 minus u to the 5th over 5 plus a constant. That's sine cubed of x over 3 minus sine to the 5th power of x over 5 plus c. Okay, that's it for that one. All right, so one more involving sine and cosine. This one we see we have cosine to the 4th power of x dx. So we don't have an odd power of terms. So we're not going to be able to set aside a term. And so for this one, we need to use this identity. Cosine squared is 1/2 1 plus cosine of 2x, right? So again, this is exactly the situation we described up here. So what I'm going to do first is go, well, this is cosine to the 4th power, but the 4th power is the same thing as saying cosine squared squared. So this becomes the integral of 1/2 times 1 plus cosine of 2x, all squared. And since this is a product of 1/2 in this expression, we can apply the square to both terms and get 1/4 times 1 plus cosine of 2x squared. Okay, so we put the 1/4 in front of the integral, and we're going to have to multiply out this 1 plus cosine of 2x squared. And I'm going to skip writing that out explicitly. That gives us 1 plus 2 cosine of 2x plus cosine squared of 2x dx. Of course, we have a little problem because we have another squared term for cosine. So the thing I want to point out is if I look at this formula, this is a kind of a common mistake or misunderstanding, place where students get stuck. This formula really in this context maybe should be written as cosine squared of theta is 1/2 1 plus cosine of 2 theta, where we don't care what theta is, as long as in the right-hand side of the formula, I double it. So in this case, the theta is 2x, so I need to double that when I apply this formula. So that's going to be 1/2 1 plus cosine of 4x, 2 times the theta I already had. Okay. And now we got to do a little bit of cleanup here before we can integrate. So I've got 1 plus 1/2, right? I distribute that, I'm going to get 1/2. So I'm going to get 3/2 plus the 2 cosine of 2x. That's my second term there. And so I got the 1/2, and now I've got 1/2 times cosine of 4x. Did not mean to write d theta there. That should have been x. I was talking about theta at the moment, so sorry about that. Okay, so where were we? 3/2 plus 2 cosine of 2x plus 1/2 cosine of 4x. Now, each of these expressions would require a u substitution, but again, it's just a constant multiple, so that one's pretty easy to do in our heads. So I'm just going to do that. Okay, the antiderivative for 3 over 2 is just 3 over 2 times x, plus 2. The antiderivative for cosine is sine, but I got to divide by that constant for the u substitution. And then cosine of 4x, so the antiderivative is sine of 4x divided by the constant 4, plus c. Now I'll go ahead and distribute that 1/4 and simplify everything a little. First I can clean this up. 2 over 2 is just 1. So this becomes 3/8 x plus sine of 2x over 4. This would be 1/2 times 1/4. That's 1/8 times 1/4. It's 1 over 32. So sine of 4x over 32 plus c. Okay, so that's it for that one. Now let's move on and talk about integrating powers of tangent and secant of x. So this one's a little different. We've got to use these identities. Secant squared of x is 1 plus tangent squared of x, and tangent squared of x is secant squared of x minus 1. They're still Pythagorean identities, but they look slightly different than the ones for sine and cosine. And we also have to think about what the derivatives for these functions look like. So the derivative for tangent of x is secant squared of x, and the derivative for secant of x is secant of x tangent of x. So that makes this process quite a bit different than the process for sine and cosine, because I need to set aside, if I'm going to do a u substitution of tangent of x, I need to set aside a secant squared of x for my du portion. And if I'm going to do u as secant of x, I have to set aside a secant x tangent of x for my du. So that's what this says here. If secant of x has an even power, then save a factor of secant squared of x and replace the other even powers of secant squared of x with 1 plus tangent squared, then substitute u equals tangent of x. If tangent of x has an odd power, right, then we save a factor of secant of x tangent of x and use tangent squared to rewrite all the remaining tangent factors with secant squared of x minus 1, and then substitute u equals secant of x. But again, we know these derivatives for tangent and secant, so if we just think about those derivatives, that tells us, depending on what kind of u we're going to pick, which of these things we need to do. So I look at this case and I see, okay, tangent is an even power, so that's not going to work, because if I was doing u as tangent, or if I was doing secant of x, tangent of x, I wouldn't be able to have that for my du. So I can't pull off a factor of tangent and secant. But the secant has an even power, so I can pull off a secant squared term and replace all the others with my Pythagorean identity. So that's what we're going to do. We're going to rewrite this as tangent to the 6th power of x times secant to the 4th power of x times secant squared of x dx. So that tells us we're using this as our du. And that means I need to replace all the rest of my terms so that they look like tangent of x. So I'm going to have to rewrite the secant to the 4th power of x term. So this becomes the integral of tangent to the 6th power of x times secant squared of x squared times secant squared of x dx. And now I can apply my Pythagorean identity, because I know that secant squared of x is 1 plus tangent squared of x. And that's going to let me do the u substitution. U equals tangent of x. Du is secant squared of x dx. And u to the 6th. This becomes u to the 6th times 1 plus u squared times du. Now we've got to do a bit of algebra here before we can evaluate the integral. This becomes u to the 6th times 1 plus 2u squared plus u to the 4th du. And now I distribute the u to the 6th. This becomes u to the 6th plus 2u to the 8th plus u to the 10th du. And find the antiderivative. That's u to the 7th over 7 plus 2u to the 9th over 9 plus u to the 11th over 11. And finally, we substitute back in like normal. And we're done. Okay, so of course those strategies aren't going to cover every situation, so we might have to think outside of the box. And this is a particularly tricky one. The integral for secant of x dx. Now this is a trick that I wouldn't expect someone to come up with off the top of their head, having never seen it before. But once you see it, hopefully it'll be easy enough to recognize it in the future. So here, this doesn't fit either situation. I don't have an even power of secant or an odd power of tangent. I just have secant to the 1st power. And so what I'm actually going to do in this case is something very clever that I'm sure the first person to figure it out took many, many months of trying things before it popped out. I'm going to multiply by secant of x plus tangent of x on the top and bottom. So of course I'm really multiplying by 1, but I'm doing it in such a way that I'm going to get an expression I can do a nice u substitution for. And that u substitution is u equals secant of x plus tangent of x. So if we take a look here, du, derivative of secant of x is secant of x tangent of x. And the derivative of tangent is secant squared of x. So notice that the terms I multiplied here, if I distribute this secant of x up top, I get secant squared of x plus tangent of x dx over secant of x plus tangent of x. So that's perfect. My numerator is the same thing that I have for du here. My denominator is u. So I do my u substitution. This is du over u, which the antiderivative is the ln of the absolute value of u plus c. And so this is ln of the absolute value of secant of x plus tangent of x plus c. Now, this particular integral shows up quite a bit later on in some of the sections where we start applying these integration techniques. So it's very valuable to make sure you commit this one to memory. I do want my students to know how to find this integral, but this is one of those ones that comes up enough that you should also have it memorized. Now, as far as other integrals that are valuable to memorize, these following integral formulas will come in handy, at least fairly often in the course. The integral for secant cubed of x dx is 1/2 secant of x tangent of x plus the natural log of the absolute value of secant of x plus tangent of x. The integral of cosecant of x dx is ln of the absolute value of cosecant of x minus cotangent of x plus c. And the integral of cosecant cubed of x dx is 1/2 times negative cosecant of x times cotangent of x plus ln of the absolute value of cosecant of x minus cotangent of x plus c. Whew. Okay, how do we get these? For this middle one, the cosecant one, it's the same basic approach as for secant of x. But of course, we'd be multiplying by cosecant of x minus cotangent of x divided by itself. So it'd be the same basic idea here. And for these two, secant cubed and cosecant cubed, you have to apply integration by parts by first rewriting this as secant squared of x times secant of x dx. Now, I'm not going to do that just because there is a lot of content in this section, and if I go through and do all of these, I'm going to end up spending a whole lot of time on this section, but I strongly encourage you to sit down and try to work out this formula yourself by starting with this rewriting and working out the integration by parts for it, keeping in mind that you know the antiderivative for secant of x, so that's probably what you want to pick for your dv in your integration by parts. And this, for cosecant cubed, it's the same basic approach as that for secant cubed, but again, dealing with cosecant and cotangent instead. Okay, so one other thing I want to mention, which I didn't mention explicitly in the notes, is that I didn't talk about cotangent and secant of x explicitly, but of course, I know very similar identities for cotangent and cosecant, right? 1 plus cotangent squared of x is cosecant squared of x, and so cotangent squared of x is 1 minus cosecant squared of x, and I also know that the derivative of cotangent of x is negative cosecant of x squared, and the derivative for cosecant of x is negative cosecant of x times cotangent of x. In other words, the approach for cosecant and cotangent is literally identical to the approach for tangent and secant. It just replaced tangent and secant everywhere in here and the appropriate derivative formulas, and it works the same way. Okay. Moving on to our next topic, trigonometric substitutions. Now, generally, I think this is probably one of the most challenging topics for students, and it's pretty understandable. It's a pretty tricky topic, but with lots of practice, you can get really good at it, and it becomes very natural. This is a type of thing that comes up sometimes in differential equations. I've seen plenty of problems where trigonometric substitutions are important. But what we're going to do here is first go through an example of the idea of trigonometric substitutions, and then we'll talk in more detail about the general concept. So here, I have the square root of 9 minus x squared. And the problem here is this minus in between the 9 and the x squared. We can never separate a square root when you've got a plus or minus between the terms. But of course, we can separate a square root on products of terms. And so we'd like if we could rewrite this expression to get rid of this square root, because that'll make the integral easier to deal with. Okay, so how do we do that? Well, we can think about some trigonometric identities that we know. And in particular, there are 3 trigonometric identities we use for this particular process of trigonometric substitutions. There is the identities involving tangent and secant. So we know that tangent squared of theta plus 1 is secant squared of theta. And we know that secant squared of theta minus 1 is tangent squared of theta. And we know that 1 minus sine squared of theta is cosine squared of theta. Now, of course, these are not the only ways that you can rewrite your trigonometric identities. We've got the identities involving cotangent and cosecant. We could write 1 minus cosine squared of theta is sine squared of theta, but these are the ones that we use when we're doing trigonometric substitutions. They're just sort of the traditional choice for the trig substitutions, so that we don't have 5 million different ways of solving the same problems. So the whole point here, though, is to notice that what this left-hand side looks like, right? You're taking a sum and a difference of terms, and you're turning it into a single squared term. So anytime you see something that looks kind of like u squared plus 1, or u squared minus 1, or 1 minus u squared, you might be able to use one of these trigonometric identities to turn a sum or difference into a single term squared. That's the whole goal here. So if we take a look at this expression, I have 9 minus x squared. It's not exactly what I want. I want like 1 minus u squared, but it's pretty close. So we try to think about how we can adjust this slightly so that I'll still be able to get what I want. And I realize that, hey, if whatever I substitute in place of x, if when I square it, I get a 9 in front of it, I'll be able to factor out the 9. That's the thought process here. So I think, well, what squared is 9? That's just 3. So I'm going to let x be 3 times, and I look at the form 1 minus u squared, so I'm going to pick sine of theta as my u. So x is 3 times sine of theta. And so then how would I replace dx? Well, I would notice that dx would have to be 3 times cosine of theta d theta. And now I'm going to go ahead and substitute all this stuff into my integral and see what happens. So this becomes 9 minus, and since I'm squaring my x, I get 9 sine squared of theta all over x, which is 3 sine of theta, and my dx is 3 times cosine of theta d theta. I'll do a little simplifying as I go. 3 over 3 cancels. And now in my square root, I can factor out the 9, and I get 1 minus sine squared of theta. Outside the square root, we still have cosine of theta d theta, all over sine of theta. And now this was the whole point, was getting this into the form where I had this 1 minus sine squared of theta, so I can replace it with just cosine squared of theta, and then I have a product in my square root instead of a difference. And that's going to let me just evaluate the square root nice and easy. Okay, so we got the square root of 9 times cosine squared. So that's 3 cosine of theta times cosine of theta d theta over sine of theta. Okay, so now we have to figure out how to deal with this integral, 3 times cosine of theta times cosine of theta over sine of theta. And that's a little tricky. What we're going to do first is rewrite the cosine of theta times cosine of theta as cosine squared of theta. Now, oftentimes with these trigonometric integrals, or integrals involving trig functions, there might be a few different ways we could apply this. You may see something else that you want to try, and that's totally fine. Again, often there's a lot of ways to solve these. But cosine squared of theta, I can replace with 1 minus sine squared of theta. And this put everything in terms of sine, so let's see what we can do. So I pull that 3 out of my integral, and then I have 1 over sine of theta minus sine squared over sine of theta, which is just sine of theta, d theta. And 1 over sine of theta is cosecant of theta minus sine of theta d theta. And well, look at that. The integral of cosecant of theta, it's a good thing we talked about that just earlier, is ln of the absolute value of cosecant of theta minus cotangent of theta. Minus the antiderivative for sine, which is negative cosine. And don't forget your plus c. Now, a little warning, this is often a place where students will make a little mistake and they'll kind of stop. Because you get used to, once you've evaluated your antiderivative, you're just done, most of the time. But here, we did a substitution, and we have to substitute back. But it's a little bit trickier because this substitution involves functions. So we have to figure out how to replace our functions back in terms of x, right? So this is the information we used for this substitution. X is 3 times sine of theta. So we're going to have to do a little bit of work off to the side. So x is 3 times sine of theta, which means x divided by 3 is sine of theta. And so I can draw a triangle corresponding to this using my trig identities, right? Sine is opposite over hypotenuse. Put theta here. Call that the opposite. That's the hypotenuse. And then I just need to solve for this side. So Pythagorean theorem, z squared plus x squared is 3. So z is the square root of 3 minus x squared. That should be 3 squared. Oops, 3 squared minus x squared. Okay, so let's see, where were we? Z is the square root of 3 squared minus x squared, or in other words, the square root of 9 minus x squared. And now I have 3 trig functions I need: cosecant of theta, cotangent of theta, and cosine of theta. Cosine of theta, that's going to be the adjacent over hypotenuse. So that's the square root of 9 minus x squared over 3. Cotangent of theta. Well, tangent is opposite over adjacent, so cotangent is adjacent over opposite. So that's 9 minus x squared over x. And finally, what else did we need? We needed cosecant of theta. But cosecant of theta is actually 1 over sine of theta. So I can just look at sine of theta and take the reciprocal. I don't even have to look at the triangle for that one. And now I can substitute all this stuff back in and get 3 times the natural log of the absolute value of cosecant of theta. is 3 over x minus cotangent of theta is the square root of 9 minus x squared over x absolute value plus cosine of theta, which is the square root of 9 minus x squared over 3. Plus c. Okay, so pretty challenging problems in general, but we're going to go through several examples here. The biggest thing is to make sure that you understand how to pick the trigonometric substitution. I really think that that's half of the battle, picking the correct substitution and substituting it in, and the rest is challenging, but it's a lot of stuff that you've done before in bits and pieces. Now we're just tying all those bits and pieces back together. So conceptually, this is a little bit tricky because instead of replacing a whole function with a new variable, we're replacing a variable with a new function. So we call this process an inverse substitution. And of course, as we saw, we need to convert back to our original variable. And that implicitly requires restricting the domain of the trig functions so they're invertible. So that brings me to something that I did and I didn't really talk about it much. I just said that the square root of cosine squared of theta is cosine of theta. But when I take a square root of a squared variable expression, I generally need to put plus or minus. However, when we do these substitutions, we restrict ourselves to the domain where the function is invertible. So in this case, we restrict ourselves for when we make our substitution for sine to negative pi over 2 to pi over 2. And that means cosine is always positive on that restriction. So when I take the square root, I know I get the positive number. So that's an important part of the approach. Now, where do we use this approach? Usually to eliminate pesky square roots. But there can be other situations where it's useful, and I'm sure you will see some of those. So let's summarize what we've got here. So how do we decide which function to substitute? Well, we look at these Pythagorean identities. 1 minus sine squared of theta is cosine squared of, that should be theta. Oops. Little typo there. So 1 minus sine squared of theta is cosine squared of theta. And so the type of expression we're looking for is 1 minus x squared. The substitution we would do is, well, x lines up with the sine of theta, x is sine of theta. 1 plus tangent squared of theta is secant squared of theta. So 1 plus x squared is the type of expression we would use this substitution of x equals tangent of theta on. And secant squared of theta minus 1 is similar to x squared minus 1. So we use x equals secant of theta for those types of expressions. Now, if the expression contains a different constant instead of 1, we change our substitution slightly. So if we have a squared minus x squared, we just replace x with a times sine of theta instead of just sine of theta. And then when we do that substitution, we get a squared sine squared of theta. So that a squared factors out, and the 1 minus sine squared becomes cosine squared. So the only difference between these situations where you have a squared minus x squared, or a squared plus x squared, or x squared minus a squared, the only difference is that you multiply the substituting function by a. And last bit of summary on this is just to look at this table. That's basically the same information, but we've also got our related triangle here. And we've also got our restriction written down. So when we're substituting sine of theta, we restrict theta to negative pi over 2 to pi over 2. When we substitute tangent of theta, we do the same restriction as for sine. Another typo though, that should be a strict inequality. There should be no equal sign there. Sorry about that. And for secant of theta, our substitution should be theta from 0 to pi over 2, including 0, and pi to 3 pi over 2, including pi. Okay. Now that we're done with that one, let's go ahead and tackle another example. So the big thing that I want to emphasize is that you're not really going to memorize these. These are, I think, a useful reference in your notes to double check if you're doing something correctly, but you're not going to memorize all of this information, at least not in this format. But if you connect the pieces together, you'll be able to get all of that information. So what do I mean? What I mean is whenever I'm looking at these expressions, I can always write down those Pythagorean identities, the 3 key ones, to figure out what my substitution should look like. So I know, okay, well, I've got 1 plus tangent squared of theta is secant squared of theta. Got secant squared of theta minus 1 is tangent squared of theta. And we got 1 minus sine squared of theta is cosine squared of theta. And I go, okay, well, which one of these has the right shape for the expression in our function? T squared minus 25. Variable squared minus number squared. Well, that's got to be this one, right? Secant squared minus 1. So I'm going to make my substitution t equals secant of theta, except since it's not minus 1, it's minus 25, then I'm going to multiply the secant of theta by 5, so that when I square t, I'll get a 25. All right, well, if t is 5 secant of theta, then dt is 5 times secant of theta tangent of theta, d theta. And, well, let's dive in. We replace dt, we get 5 secant of theta tangent of theta, d theta, over t squared. Well, t is 5 secant of theta, so this is 25 secant squared of theta, times the square root. And again, t squared is 25 secant squared of theta, minus 25. And now we'll do a little algebra. So the 5 over 25 simplifies to 1/5. Secant of theta over secant squared cancels one of the factors, and I'll get left with just secant. So this becomes tangent of theta d theta over secant of theta. And down here, I factor out the 25 times secant squared of theta minus 1. Now I replace my secant squared of theta minus 1 with tangent squared of theta using my trig identity. And again, we know the square root of tangent squared is going to be positive because we talked about those restrictions on the variable here. So this is secant of theta times 5 times tangent of theta. And so the tangents cancel. Couldn't ask for it to work out much nicer than that. I pull the 1/5 in front, and 1 over secant of theta is the same thing as cosine of theta, d theta. So this works out really nicely. The antiderivative for cosine is sine of theta plus c. So now all we got to do is figure out how to substitute back to our original variable. So we already knew that t was 5 times secant of theta. So that means t over 5 will be secant of theta. And since I tend to think about my triangles in terms of sine and cosine, I'll rewrite this as cosine of theta is 5 over t, because remember, cosine is just the reciprocal for secant. Now I'll draw my triangle. Put theta here. Cosine is adjacent over hypotenuse. Call this other side z. And solve for it. 5 squared plus z squared is t squared. So z is the square root of t squared minus 25. And so what is sine of theta? Opposite over hypotenuse. That's the square root of t squared minus 25 over t. So now I go back to my integral, replace it with my expression in terms of t, and we're done. Okay, moving on. Let's go ahead and tackle another example here. So I got to go through the same thought process, but here I got x squared plus 9, and that looks a lot like tangent squared of theta plus 1 is secant squared of theta. So I go, okay, I'm going to let x be tangent of theta, but remember I got this 9 here, so I'm going to multiply it by 3. And then I also need my dx, and so dx will be 3 times secant squared of theta d theta. And we can start substituting. We get 3 tangent of theta for x. My dx I can replace with 3 secant squared of theta d theta. And down here, x squared will be 9 tangent squared of theta plus the 9 that was already there. So up top, 3 times 3 is 9. This becomes 9 times tangent of theta secant squared of theta d theta. And in the denominator, we factor out the 9 and get tangent squared of theta plus 1. Now we can apply our identity here. That gives us the square root of 9 times secant squared of theta. Square root of 9 is 3, and the square root of secant squared is going to be secant. Again, for all these problems, we can just take the positive root. And now we can simplify a little bit. 9 over 3 simplifies to 3. So I'll pull that out in front. We get left with tangent of theta, and secant squared divided by secant is just secant to the first power of theta. And we know that the antiderivative for tangent of theta times secant of theta is just secant of theta. So I need a plus c there. Now, I'll show an alternative way. I've shown setting up the triangle a couple times here. Sometimes you get really nice, the functions work out in a really nice way to where you can actually use those Pythagorean identities to identify your substitution back in. So I know that x over 3 is tangent of theta. And I also know that secant squared of theta is 1 plus tangent squared of theta. So I can substitute that back in, and I get secant of theta is the square root of 1 plus x over 3 squared. Though that's not with how we would write it. So I'd have to do a little algebra here to rewrite this. With that in mind, maybe I'll use the triangle just because that algebra can be a little messy. But sometimes it works out nicer than this, and you can go through and use those identities to do that. Okay, my eraser does not want to work. Let's try that again. There it goes. So I'll just draw the triangle. Theta, tangent is opposite over hypotenuse, solve for the other side, and I'm just going to kind of do this one in my head. X squared plus 9. And so secant of theta is 1 over cosine, so it's the square root of x squared plus 9 over 3. So that's completely equivalent to the expression that we found before using the identity, but it does look a bit different, and this way does work out a little cleaner. So 3 over 3 cancels, and we get the square root of x squared plus 9 plus c. Okay. That's it for that one. And now we got one more example here. So this is a particularly tricky problem. Evaluate the integral of cosine of t dt over the square root of 1 plus sine squared of t. Now this one's tricky because it looks a lot like we need to do a trig substitution, but there's already trig functions here. And there's nothing I can do about the square root of 1 plus sine squared of t. If it was 1 minus sine squared of t, that'd be great. But there's nothing I can do about it in the current form. So what I'm going to do is first do a u substitution. U equals sine of t, then du equals cosine of t dt. And that gives me the square root of du, or the integral of du over the square root of 1 plus u squared. And now I can do a trig substitution on this. So I see 1 plus u squared. That looks a lot like 1 plus tangent squared of theta equals secant squared of theta. So I'm going to let u be tangent of theta, in which case du will be secant squared of theta d theta. So we get secant squared of theta d theta over the square root of 1 plus tangent squared of theta. One plus tangent squared of theta is secant squared of theta. So this becomes secant squared of theta over secant of theta d theta, and that simplifies to the integral of secant of theta d theta. Now we already know the formula for that antiderivative, so we get ln of secant of theta plus tangent of theta plus a constant. But now we have to do 2 rounds of substitution to get back to our original variable of t. So the first substitution I've got to do is to get back in terms of u. So I've got secant of theta and tangent of theta. So this time it is going to be easier to use the identity here because I've already got that tangent of theta is u, and I have that 1 plus tangent squared of theta is secant squared of theta. So in this case, we can write that secant of theta is the square root of 1 plus u squared. So I don't have to draw out the whole triangle this time. And now, last step is just to plug u back in. So u was sine of t. And we're all done. All right, well, that's it for our video on trigonometric integrals and substitution. Thank you for watching.